Right, so now we're going to talk about quotient manifolds. And one motivation for studying the notion of quotient manifolds is if you're working with, for example, the Grassmannians, which are, it's like the set of p-dimensional subspaces of a larger dimensional space. Okay, and of course, what typically happens, it's like when you work with Grassmannians, is that you look with, you sort of manipulate it's like elements of Grassmannians by looking at representative elements, which consist of elements, say, of the Stiefel manifold, where you have, say, p sort of n vectors is like which are linearly independent, okay, and then of course that spans a p-dimensional subspace. But of course the problem is that there is some non-uniqueness in that representation, because there could be many, it's like p vectors which span the same p-dimensional subspace. Okay, so when we want to then work with the idea, it's like that if you have a p-dimensional subspace generated by, say, p vectors, that as long as the subspaces are the same, then it's equivalent. Okay, so let me try to be a little bit more precise here. So let's say we have a manifold M. Okay, and we want to equip it with the idea of an equivalence relationship. Okay, and this is oftentimes denoted by a tilde. Okay, so this is a relationship that has the following properties. So the first thing is that it's reflexive. Okay, so that means that X is equivalent, it's like to itself, okay, for all X in the manifold. The second thing is that it's symmetric. Right, so X is related to Y, right, if and only if Y is related to X. Okay, and this is true for all X, Y manifold. And the third thing is that it's transitive, which basically says that if X is related to, okay, so if X is related to Y and Y is related to Z, then X is related to Z, and this is again true for all X, Y, and Z on the manifold. Okay? All right, so these are, I mean, sort of fairly natural things. It's like sort of axiomatic properties. It's like of an equivalence relationship, right? So if you say X is, you want obviously X to be equivalent to itself, then that if X is equivalent to Y, that also means that Y is equivalent to X. And if X is equivalent to Y and Y is equivalent to Z, then X is equivalent to Z. Okay, so these are the three main properties. Then you can look at what is known as an equivalence class. So the equivalence class often denoted by a square bracket, right, is the set of points Y in the manifold with the property that Y is related to X. So the equivalence class of X is the set of elements in the manifold which are equivalent to it. Okay, and then with that we can now look at the set of equivalence classes, right? So the set sort of M quotiented by the equivalence relationship, right, is the set of equivalence classes, okay, on manifold. Okay, so the basic idea is that if you have an equivalence relationship, then what that does is to essentially partition the elements of the manifold into equivalence classes. Okay, and And if you just look at this set of equivalence classes, then we say that that is the quotient, right? It's the quotient of M by the equivalence relationship. Okay, so again, it's like this set consists of this set of equivalence relationships. Each element of this set is again a subset, it's like of the manifold, okay? And there's a natural or canonical projection from the manifold to the quotient. Right, there's a natural or canonical projection pi from the manifold to this quotient given by sort of the obvious thing. So it's given by the map from X. It's like where you map X to the equivalence class. It's like containing X. Okay. So, all right. So clearly, right, by construction, right, if pi of X is equal to pi of Y, if and only if X is related to Y. So what that means then is that if you want to look at the equivalence class associated with X, what you can do is you can first project, you first project X to the equivalence class. Okay. And then you take its preimage. Okay. All right, so, and you might think that seems a little bit redundant, and that's because I would like to think of this thing as an element of M quotiented by the equivalence relationship. All right, and then this thing here, where you take the preimage, then is a subset of M. Okay, so there's a slight conceptual distinction, if you will, between the two. All right. Anyhow, so that's just a bit of terminology. Then M is said to be the total space of the quotient. Right. M is the total space of this quotient. Okay. All right. So again, it's like we're looking at a situation where M is a manifold, right? So let's say we have a manifold with a maximal atlas, right? So this be a manifold with an equivalence relationship. Tilde. Okay. And then we want to endow, it's like this quotient with a manifold structure. So we let B plus, right, be a manifold structure on the set M quotiented by the equivalence relationship. Okay, so the manifold. All right, so so now we have, in principle, we now have two different manifold structures. It's like one on M and one on the quotient. All right, So, so you want to ask when, um, what kind of manifold structure you should endow M quotiented by the equivalence relationship, so that this is a quotient manifold. Okay, so the manifold M quotiented by equivalence relationship endowed with some maximal atlas, right, is called a quotient manifold. If the following is true, if the natural projection right, again the natural projection is a map pi from M to M quotiented with equivalence relationship, where you map X to the equivalence class associated with X. Okay, if this thing is a submersion. Okay, all right, so in that situation then it's like there is we say that this is a quotient manifold. Okay, all right, so let's state a few propositions about this. So the first proposition says basically that this quotient, this manifold structure which makes M quotiented by the equivalence relationship is unique if it exists, all right? So let M be a manifold. So I should say the following basic idea, right? So there is the basic idea, if you will, is that it's like this pi is going to be an immersion in general. It's like, but you want under circumstances for it to be an immersion. Sorry, a submersion. Okay, and essentially what needs to happen is that the equivalence relationship needs to have some additional nice properties for that immersion to be actually a submersion. Okay, all right, and then that you actually have an honest to goodness quotient manifold. Okay, so let's say, okay, so M be a manifold, and let M quotiented by the equivalence relationship be a quotient of M. Okay, then M quotiented by the equivalence relationship admits at most one manifold structure that makes it a quotient manifold of M. Okay. All right. So if that happens, it's like then we say that the equivalence relationship is regular. Okay. In this case, oops. Okay. And we refer to the set M quotiented by the equivalence relationship endowed with the this manifold structure. As the quotient manifold of M. Okay. All right. So now it's like it would be helpful to actually characterize when equivalence relationships are regular. Okay. So question: when are equivalence relations regular? Okay. And the way you can do this is to look at what is known as the graph of the equivalence relation. Okay. So consider the graph. Tilde. Okay. So the graph is an object which is in the product of the manifold with itself. Okay, it's a set. So the graph of this tilde, right, is defined to be the set of points x, y in M cross M, right, with the property that x is related to y. So if instead, for example, you had a function, it's like f mapped from x to y, right, then the graph of that function f is the set of points x and y in it's like the spaces, it's like x cross y with the property that y is equal to f of x, right? So that's the usual notion of a graph which you're familiar with, and this is sort of the natural analog of that, where you think then of the equivalence relationship as a relationship again between 2 points on the same manifold. Okay, so you consider this graph, then you want this graph to have, well, the point is that it's like the equivalence relation is regular if and only if the graph has the following set of properties. Okay. All right. So let's try to characterize when an equivalence relation is regular. And again, it's like when you have a regular equivalence relation, then there is this, then the canonical projection is a submersion. It's like, and there's a natural manifold structure on the quotient sets. Okay, so let me state a proposition. So an equivalence relation tilde on a manifold M, right, is regular which means that M quotient tilde is a quotient manifold. Right, if and only if the following conditions hold. So you need all the conditions to hold. Okay, so the first one is that the graph tilde is an embedded submanifold. Okay, of the product manifold. M cross M. Okay, so the second thing is that the projection into the first slot pi pi1, which is a map from the graph tilde to M, which is obtained by the following: pi1 x y is equal to x. This is submersion. And the third property is that the graph is a closed subset of M cross M. Okay, where M is endowed with its manifold topology. Okay, so you endow M with the manifold topology, and then that induces a topology on M cross M. Okay, all right. So if all these conditions hold, then again, M quotiented by equivalence relation is a quotient manifold, and you can also see that the dimension of M quotiented by the equivalence relationship is given by dimension M quotiented tilde is equal to 2 times the dimension of M, right, which is of course the dimension of M cross M, minus the dimension of the graph of the equivalence relationship. Okay, all right. Yes. So let's try to understand what these three conditions come from, and again why they're important. Okay, so I'm going to state another proposition. I can at least try to explain what these three conditions show up. So the proposition is that it's as follows. So conditions 1 and 2, right, where I literally mean these two propositions, are necessary and sufficient for the quotient, right, to admit an atlas. That makes sort of the canonical projection a submersion. Okay, and then such an atlas is unique. And the atlas topology is identical to its quotient topology. Okay, then the third condition is necessary and sufficient. Right, for the quotient topology to be Hausdorff. All right, and then so now then we were in a position to state yet another proposition, which again comes from the fact that the natural projection, it's like, which we have is by definition now is submersion. Okay, so so you can use essentially the canonical projection to show that it's like the set M quotiented by tilde, right, is an embedded submanifold, right? So proposition, right? So let M quotiented by the equivalence relationship be a quotient manifold of the manifold of a manifold. M, and let pi be the canonical projection. Okay, so if the dimension of M quotiented with equivalence relationship is strictly less than the dimension of M, then each equivalence class pi inverse pi x, okay, for every x in the manifold, right, is an embedded submanifold of M. Of dimension of M minus the dimension of M quotiented equivalence relationship. Again, this is just a natural application. It's like of the submersion theorem, right? Because we already said that if you have a regular relationship, right, then in particular the canonical projection is a submersion. Okay, so taking the pre-image of that gives you an embedded submanifold by the submersion theorem. Okay. And then, as is the case, it's like if you're working with M being the space of matrices, for example, right, then you could have a matrix quotient manifold. Okay. And in particular, let me say a little bit about the Grassmann manifold, which is perhaps the most important example, it's like of a quotient manifold in the case of the matrices. Okay. So anyway, so let's see now. So anyway, so when M is say Rn cross P, right, or a submanifold, of Rn cross P, right, we call M quotiented by an equivalence relationship as a matrix quotient manifold. And then, and then more generally, it's like we're also interested in matrix manifolds, right? So examples of matrix manifolds include the non-compact Stiefel manifold. So here's the non-compact Stiefel manifold. There was the orthogonal Stiefel manifold. Right, there's the Grassmann manifold. So again, the Grassmann manifold is basically the set of p-dimensional subspaces. It's like in this n-dimensional space. And as I sort of alluded to, what happens is that you can relate this to the orthogonal Stiefel manifold, right? Because the orthogonal Stiefel manifold consists of, it's like p n vectors, like which are orthonormal to each other, right? And obviously they span a p-dimensional subspace. So put another way, if you want to think of the Grassmann manifold as a quotient manifold, you can think of it as a quotient manifold of the orthogonal Stiefel manifold, where the equivalence relationship more or less says, well, let's look at this, n by p matrix, and you look at the column space associated with it, and if the column spaces are the same, then we say that the two elements of the orthogonal Stiefel manifold are equivalent to each other. Okay, and if you quotient the orthogonal Stiefel manifold by that equivalence relationship, you get the Grassmann manifold. Okay, and a few other examples, which we'll talk about as we go along. But these again are some examples of matrix manifolds. In particular, it's perhaps one of the most important examples of a matrix quotient manifold is the Grassmann manifold, consisting of all p-dimensional subspaces. Okay, so let me just stop here for now.